We are doing the Unit 8 review in preparation for the quiz that's coming up. So before we get to number 1, I think what we should do is sort of just how exactly to do these kinds of problems. So we'll take this one, for example. Set up integrals but do not solve to find the volume of the solid generated by revolving the region bounded by y equals x cubed over 2 and y equals 4 and the y-axis in the first quadrant about, and then there's a few different lines to rotate it about. So first, how do we solve solids of rotation? If the solid of rotation doesn't have a hole in it, which means, all right, so we'll ignore number 1 for now, but let's say, yeah, we'll do the absolute value of x. So let's see if I can put a graph in here. All right, so there's our graph. Y equals rad x. Y equals rad x. And we'll just say this is the end. So we're revolving this around the x-axis. So if you look at it like a 3D view, or I guess I can try, maybe I'll do it in red, to do something like this. Sort of an orthographic view. Oh, that's really bad, but you get the idea. That it's sort of rotating, and then if we draw like a 3D view, it's kind of like, and then this is the this is the axis. Where's the black? Oh. And it comes out of the center here. So there's no hole in the middle of this. So we can use the washer method. So that's the first step. Ask yourself, is there a hole in the middle of the solid of rotation? If there is not a hole, it's a little bit easier. We'll use the washer method, where basically we turn this into washers. So we're basically like approximating the area or the volume by using these cylinders, these washers. And these are 3-dimensional. It's kind of like, oh, I don't know if I can draw this, but it's kind of like this, and then there's one behind it. There's one behind it, kind of like that. And these washers are like analogous to the rectangles in the Riemann sums. If you remember, let's say we have the graph of, we'll do y equals x, the cube root of x again. We have little rectangle things, right, to approximate it. So we have these rectangles, and as they become smaller, they're basically like lines, right? And since you have an infinite number of these, they eventually form the entire area. So this is the same thing where we have eventually these washers become so thin that they're essentially circles, like circular pieces of paper. And if you imagine a bunch of circular pieces of paper, in making sort of this shape, you can, the volume of those circular pieces of paper approximates the volume of the solid of rotation. And as your pieces of paper get thinner, that approximation becomes better and better, just like the Riemann sums. So the Riemann sums, how we turned those from sort of individual, like a summation, into actually an integral is, let's say this is A, this is B, it's the integral from A to B of, well, it's a rectangle, right? So the area of a rectangle is base times height. Base times height. So let's focus on the height for now. All right, height times base. Height times base. The height is whatever this function is. So if this is 4, if b is 4, let's say, then this would be 2. So the height of this little rectangular piece, oh shoot. The height of that, oh my god, I can't draw a straight line. All right, I'm just gonna, just imagine the graph is still there. The height of this is 2, and that's found by, right, the y value is the height of these rectangles, or these sort of strings if they're thin enough. So that's the function, a equals f of x. And this is just assuming we're going to the area enclosed by the function and the x-axis. That's the height. And now the width, this is where the d of x comes from. This d signifies a tiny, tiny little change in x. So a little nudge in the x value. So basically, this is the base and this is the height. This is kind of a quick explanation, and if you need more, there's 3 Blue, 1 Brown on YouTube. Their calculus series, or his calculus series, is really good for getting an intuitive grasp on some of this stuff. So essentially we're doing height times base, and we're doing it a bunch of times, infinite times, which is what the integral means. So now take this up to a solid revolution. Instead of these little rectangle things, we're actually finding circles. Remember, these washers, as they become thinner and thinner, become circles. And so our area, or our volume for a, okay, that's a confusing way to phrase it. These are really thin washers, and as they get thinner and thinner, they approach circles, right, which have no height. So I guess I'll do it up here. The volume of a cylinder is pi r squared times height. So like how we went from this area to this, from one to another, we'll go from one volume to another. So now we're adding up a bunch of these cylinders, or these washers, and we'll say here. Oh my god. My apologies. Okay. Hold up. Okay. This, we'll say this part is height. And this part, this is R. So the R, if you'll notice, this is R. From here, extends up to the function, which is similar to these lines, how they extend from here to up to the function. So this is just the function, f of x. Then that's multiplied by pi, and the f of x is squared. And now the height, this part of it, is the same as the base length, or like the width here. This is because we're doing Riemann sums, right? So they get infinitely small. These get infinitely thin, which means the height approaches 0. So it's just a little change in the height. So we do dh. So hopefully that was a good sort of intuitive way to do it. And then this equals, we can use our algebra. And we get, and the x is the same as the h. This was just to clarify what exactly it was referring to. So yeah, hopefully that helps for these problems. So we're kind of looking for something like this for the washer method. And then obviously if this is assuming it's the x-axis, if it's a different function, then it's just minus the other function. So if we go over here, f of x minus g of x squared dx. So now let's do number 1 with that information. Okay, so, and then the first one is about the line x equals 0. So let's draw our picture. I'm going to use this because I can't draw straight lines. So y equals x cubed over 2. So x cubed is something like this. Oh, whoops. Like that. And y equals 4. So there. And we're revolving this around x equals 0. So like this. And it's kind of like this circle thing. So we just use our formula and we get, well, here, I'll try and do it like not just using the formula. This time the circles are parallel to the x-axis, so the r is actually horizontal, which means we have to rewrite things in terms of y. So instead of going y equals x cubed over 2, we say 2y equals x cubed and x equals the cubed root of 2y. So that is this. This is the same. These two are the same, and they're both referring to this part. And so that is our radius. So we'll take that. And it's pi r squared. So pi radius squared. And then we take our integral from this bottom part to this top part, which is from 0 to 4. 0 to 4, and dy. So then we can just simplify if you want a little bit. There's not really much to do. and that's number 1. So these ones, once you get down to like the formula and an understanding of why the formula works, they're pretty straightforward. Now, if there's a hole in the solid of revolution, I think that's what they're called. So instead of just going to x squared, we'll go x squared and, I don't know, 1/4 x or something like that. Or this is the square root of x, and this is 1/4 x. Now we're finding this. And so when we rotate this, it's going to look something like this. And it's going to have a little hole things down the middle. And this will be our axis. So how do we address this hole? Well, going back to our idea that this is just washers, it's basically just, if you take this big part and find the volume of this, and then you subtract out this smaller part, find the volume of the hole, you have the volume of just the washer. So what we can do is, we'll call this big R, like Grabowski does. And then this smaller one is small r. So the bigger radius, or the bigger cylinder, would be pi r squared times height minus pi little r squared times height. And then we want to integrate it. So we go pi r squared minus pi small r squared and dh. And then we can factor out the pi. So we could just go like this. Oh wait, no, minus dh. And this is our formula for if there's a hole. If there's a hole in the slot of revolution. This is the washer method. So that's for something like the rotating about the line of y equals -2. Our graph looks something like it's still x cubed, and and this y equals 4. But this time we're rotating about y equals -2 down here. So when we rotate that, the shape comes down right about here-ish. And it's sort of this thing. Ooh, this does not look very pretty, but with this hole in the middle. So when we have that, that's just the washer method. This is our big R. This is our small r. So big R is, well, this is 4, and this is -2. So big R is 4 minus -2, or 6. 6, and then small r is just 0 minus -2, which is 2. So then we can just, or that's just for this circle. So then if we want to generalize this to all the circles, or to all the washers, it's f of x, which is y equals 4 is the first one. 4, it's still 4. 4 minus -2 is 6, and then small r is x cubed, x cubed over 2, and then minus -2, and that just equals x cubed over 2 plus 2. So then plug that into our formula. And we're going from 0 to 2, because these functions meet at the point 2, 4. So 0 to 2 of big R squared minus small r squared and times pi and dx. So that was the first half of number 1. There's 2 more, but it's the same concept, so I'll just skip those. So number 2, set up but do not solve the integrals to find the volume of the solid if the base is bounded by the circle x squared plus y squared equals 4. So this is a circle, which does add a bit of extra work, but it's not too bad. And then this is at -2, 2, 2, -2. And then, this is also the base. So for these, I don't know, I feel like my explanations are just more confusing. So maybe I'll skip like how we get the formula and just say, so for the first one, rectangles of height 4. So the area of a rectangle, base times height, and we'll call the base length, we'll just call it L. L times height, but height is 4, so it's just 4L in this case. And then, because we are dealing with circles, you have to split up the function into 2 parts. So the first one, cross sections are perpendicular to the x-axis, which means they're going like this. So that means we have to do this. No, this is the normal way. So first let's isolate x. Y equals 4 minus x squared, square root of all that. And you'll notice that a circle does not pass the vertical line test. And that is seen here, because if you plot this, you only get the top half of the circle. You only get this. Which means, well, there's multiple ways to do it. You can multiply the whole thing by 2, so you define like this part, and then you just multiply by 2 to find this part. Or what you could do is, mathematically it looks the same, but well, yeah, I guess it's just all the same. But you just say, y also equals the negative square root of 4 minus x squared, and that will give you the bottom half of the circle. So now all we got to do is plug in our formula, which is, we're going from -2 to 2, and we're doing 4L dx. And what is L? Well, L is this. It's these red lines are L. And how do we find those? Well, we take the top function, subtract the bottom function, and we get the top function is this, subtract the bottom function. Oh, and don't forget the 4. You can put the 4 outside. And dx. And then these are just the same, so there'll be a 2 in front of them when you simplify. You can also factor that out, and you get 8 times the integral from -2 to 2 of radical 4 minus x squared dx. So that's 2a, like the top left part of 2. Then I'll just do one more because it's pretty much the same thing once you get the concept down. I'll do the equilateral triangles one. So this time, instead of rectangles, we're doing equilateral triangles. And the cross-section is parallel to the x-axis. So this time it's like this, which means we have to do this in terms of y. So first, let's just find our functions in terms of y. And again, we got to do the negative version. And then for the equilateral triangle part, let's just find the area of an equilateral triangle. A equals, I'll draw one out. So if you have this, we'll say this part is L. And we're trying to find h, so we can use base times height times 1/2. And we know it's equilateral. So we know this, we'll divide this part into 2. So this part is L over 2 and L over 2. And then this whole thing is L. And then this, it's an equilateral triangle, so we know this is 60 degrees, this is 30 degrees, this is a 30, 60, 90 triangle. We can multiply by rad 3 to get height is rad 3 over 2, L. Now, we just do L times height, which is just, times 1/2, right, triangle formula, equals 1/2 length times rad 3 over 2, L equals rad 3 over 4, L squared. And then we'll do the integral with this from -2 to 2 of what we just found. Now we plug in L, which is the same thing that we did last time. And we'll take out the rad 3 over 4. We get 2, well, we'd get this minus this, so it's just this, since it's minus a negative, it's just this plus the positive, the absolute value of the second function, so we get 4 minus y squared, all square rooted and times 2. dy, you can factor out the 2. And you get this. Oh, and it's squared. That's, yeah, it's all squared. Oh, okay. I'll just rewrite it. Because remember that the L is squared in this case. So this, oh wait, the 2 should be inside the parentheses. This will actually just become a rad 3. And this will just become 4 minus y squared dy. So that's our formula for 2b. Now let's go to question number 3. Okay, question number 3. Set up but don't evaluate a definite integral with a single variable that would represent the area or the volume when given the region is revolved around the indicated line. So let's just draw out the indicated region first. We got x squared, and no, don't make that blue. Oh, it's been making the graph blue. Okay, here we go. X squared and 2x. Oh, I'll make this different. There we go. We're finding this. So first 3a is just find the area of the region before any rotation. That one is from last year or first semester as well, where it's just top minus bottom, right? So the top in this case is the 2x minus x squared, which is the bottom. And we're just taking the integral from 0 to, let's see, they meet at the point 2, 4. So 0 to 2, because this is with x dx. And then, yeah, just take the integral. This one we actually have to evaluate. So this is x squared minus 1/3 x cubed, like this. And then 4 minus 8/3 equals 4/3. So that's 3a. That one's just like a review of last semester. 3b, the volume if rotated about x equals 0. X equals 0 is this line. Oh no, I cannot draw a line. It's the it's the y-axis. So then it's just this. This is our sort of solid revolution. Hopefully you can picture that. It's a pretty bad drawing. This is the washer, because there's a big hole in the middle. This part's like a big hole. So we'll take our big radius, which is, since we're rotating this around a vertical line, actually we have to put these in terms of y. So x equals rad y, and x equals 1/2 y. So we go integral from 0 to 4 this time, because it's the y, of r, big R squared minus small r squared. So big R in this case is the farther out one. It's right minus left for if you're dealing with horizontal distances. So that would be rad y squared minus 1/2 y squared, and then the times pi dy. Oh, and we don't have to solve it, so that's it. You can simplify this also and get just y minus, I guess it would be y squared over 4. But yeah, you don't have to. So that one's pretty pretty straightforward. It's like number one. Let's see. And the other two are also pretty straightforward. 3C and 3D. So I will move on to problem 4, which is, oh my god. Oh wait, just do this. Genius. Nope, 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 nope. There we go. So we're using the same region, but we're using it as the base of a figure, and we're doing like the cross-section thing. So each cross-section is a semicircle, and we haven't done semicircles yet, so I'll do the semicircle. The 4B is a rectangle, and I just did that, so I'll just do the semicircle one for this problem. Each cross-section is a semicircle perpendicular to the x-axis. So I guess I'll just redraw it. And that's the base. Oh, wait. Yeah, perpendicular to the x-axis. So now we're doing area of a semicircle. And we're going to call this is L, because it's the base. This makes the base. So semicircle is just 1/2 pi r squared. And r in this case would be like this. So L is just r over 2. Or no, r is L over 2. So, which equals 1/8 pi L squared. So now we just take the integral. Since it's a vertical, we're doing like a vertical semicircles. We do the x values. So 0 to 2 instead of 0 to 4. Put the pi array on the outside. And now this is L squared. L is just the top function minus the bottom function. So 2x minus x squared. And squared dx. So that is all there is to that. Now for the final problem. Okay, so problem 5. Find the region of the area bounded by, oh, this is annoying, x equals y squared minus 4y, and x equals 2y minus y squared. So this one's kind of harder to draw a graph for, but we can still make an approximate graph. And even if you can't, it's not the end of the world. It's just a bit easier when you have something to look at. So first off, these are y squared functions, which means they're parabolas, but they're horizontal parabolas, as opposed to x squared would be vertical parabolas. And then this is a negative y squared, which means it'll face this way. And then this positive y squared will face this way. So I'm thinking they'll intersect like this, and we're trying to find this area. And then let's see, when y equals 0, x equals 0. And also when y equals 2. I'm looking at this for this one. And then this is at 4, when x is 0, y is 0, and y is 4. So this one's facing that way. So it's something like this. Oh, that's ugly. No. This is so annoying. No, don't do that. Okay. Something like this. And we're trying to find this. So I'll erase this. This is just a right minus left area thing, right? Because it's in terms of y and it's horizontal. So instead of top minus bottom, it's right minus left. And since we are going horizontal, we do the heights. So where do these meet? Where is this point? We know they meet at 0, 0. So the bottom will be 0 because the y value of this point is 0. But what's the y value of this point? Let's see. Set them equal to each other. And now just simplify. 2y squared minus 6y equals 0. So y equals 0 or 3. And since we know this one's 0, we have that one. This is 3. And then we're just doing the right function minus the left function. Right function is the one facing like this, which is the second function. So, and then that leaves the other one to be the left function, dy. And then we actually have to solve this one. So just doing some algebra, we know that this becomes this. Wait, no. That's not right. It becomes this. And then we could take out the 2, but I don't think it really matters. We'll get 3y squared minus 2/3 y cubed. And then just plug in 3, and we get, what, 27 minus 18. And 9 is our final answer. So number 5 was just a trickier area between two curves. And I don't know, I feel like it won't be on the quiz, but the other ones, hopefully this helped a little bit. And good luck on the quiz.